So today we will talk about classification. Okay. So really classification after regression is maybe, the second most fundamental task of machine learning. So if we do a quick survey, please just, can you raise your hand if you have ever heard about classification? Okay, cool, a lot of you. And now, can you keep your hands up if you have already solved a classification problem? Also a lot of you, cool. So first, let's, try to see how we can define the classification problem. So as usual in supervised machine learning, you are observing a data set S of some input xi and some output yi. But now the main difference will be that your output will belong to some set y, which will be discrete. Okay. Previously with regression, we were considering some subset of the real numbers. Now y will be a discrete set. And so what is the goal of classification? As other problem of supervised machine learning, I am giving you a new input x, and what you want to do is to predict its label y. Okay? That's the game we are playing. You have some training data, S. The yi will belong to some discrete set. You will use some algorithm. And with this algorithm, you will learn a function which will help you to do some prediction. Okay? So you see that it is exactly the same framework as for regression. The main difference is that now we are relating the input variable to an output y, which is a categorical variable. Okay, so the output y can only take some discrete values. That's the principal difference with before. And so we can consider some binary classification. In that case, the output y can only take two values. So, okay, so y will belong to two classes, C1 or C2. And what we will often do today is that we will call these classes, 0 and 1, or for example, -1 and 1. And we can also consider the multi-classification, the multi-class classification setting, where the output y can take more than two values. Okay, so then y can take the value of k different classes. So from C1 to Ck-1. And here also, we will often use the name to call these classes 0 to K-1. Okay, but what is really important to understand and to have in mind is that when we are calling, these classes 0 and 1 or -1 and 1, it's just a name. Okay, there is no ordering between the class. It's not because you have like the class 0 and the class 1 that the class 0 is smaller than the class 1, for example. Like the outputs are really categorical. So for example, you will try to see, do you have a disease or not? It's not like the fact that having a disease is smaller than not having the disease. So you have to keep in mind that this name is just for commodity, okay? It's exactly equivalent to have C1 and C2 or 0 and 1 and -1 and 1. And for some example, we will use a 0-1 case, and for some other example, we will use a -1-1, but it will be exactly the same. Is it clear for the general setting? Cool. So let's do some examples, let's start easy. So the first one is like the spam detection. I'm sure you all have like a mailbox, for example, the one of EPFL, and you can see that the spam detection is not very efficient. So here it's some mail I receive, and you can see that some of them are really expected. So for example, you will get a mail about a talk I will give soon, or you will get a mail of my admin about like the coffee we are missing in the lab. These are the mail I want to receive. And now we have other examples. For example, some mails from some predatory scientific journal who want us to publish there and we don't want, or some weird mail about Western Union, I don't know, these are spam. So what is a class we want to do in spam detection? We have a training set. And with this training set, we have learned a classifier. And now I want to use this classifier to classify my mail between the mail I want in my inbox and the mail I don't want in my spam folder. So you see that's really like a classification problem because your output will be the class 1, which is a good mail, and the class 0, which is a spam. And you see that I can call that class 0 and I can call this class 1, or I can also call the good one 1 and the spam 0. It will not change anything. Another famous example is an example of image classification. So here we have some pictures, and you want to classify between being a cat or being a dog. So as exactly as before, you had previously a training set, you have learned your classifier, and now you are observing some new pictures. And for each picture, what you want to do, you just want to say if that one, it is a cat or it is a dog. So your input are these pictures, and the output is a label. It will be the cat label or the dog label. Okay, you see it's really clear. So let's look at another example we will use a lot today. So it is a credit card default example. So we have a credit card service, and they want to determine if their clients will default on their next payment of their credit card or not. And so they have this training set of previous customers. And for each customer, they will have the income of the customer and the credit balance. Okay, so the credit balance is the amount you have on your bank account. And what they want to detect, what they want to learn is if a customer will default or not on his credit card payment. Okay? And so we see here that the customers the customer who default previously are this orange cross, and the customer who did not default are this blue circle. So this is your data set. And now what you want to do is that if you are observing the data of a new customer, for example, it could be a point here, you want to detect, you want to predict if this customer will default or not. So for this one, what do you think? Can you repeat? Again, I don't know. Cool, thanks. And if I do a point here, what do you think? It will default. So how do you decide? So what you see is that the income features is not so informative. You know, it does not really help you to detect if you will default or not. But you see that when you look at the balance, there is a clear trend. If you have a low balance, then you are very likely not to default. And if you have a high balance, you are very likely to default. Okay? So this was some example of the classification task. And so how are we doing some classification? Just some other definition. It's really using a prediction function, which is in the case of the classification called a classifier. So what is a classifier? It is a function from your input space X to your output Y. And what is doing this classifier? It is dividing the input space into a collection of regions belonging to each class. You see, you really have a function which will split the space into different regions. This will be the region of the class 2. This will be the region of the class 1. And this will be the region of the class 3. And so you see that we have some frontier between these different regions. And this frontier we will call decision boundary. Okay? So the decision boundary are really the boundaries of this region. And so when you go across a decision boundary, you go from one class to the others. So this is what is called a classifier. So a classifier is the function you will want to learn in order to do your prediction. And so you see that it's possible to have some linear classifier. So what do we mean by a linear classifier? It is a classifier for which the decision boundary are linear. But it is also possible to have some nonlinear decision boundaries. So this will give you some nonlinear classifier. And so for these, you see that the decision boundary are nonlinear. But just, want to remind you that as for regression, it was possible to get some nonlinearity only by considering some augmented feature space. So maybe, in fact, here I have the feeling that I have learned a nonlinear classifier, but in fact, I have just learned a linear classifier in an augmented space. So this will be exactly the same as for regression. It will be possible to obtain some nonlinearity only by augmenting the feature space. So now let's try to see how we can solve this classification problem. And the first thing I would like we see together today is that can we just see the classification problem as a particular example of the regression problem? Because when we look at the definition, we see that classification is just a regression problem with discrete labels. So in that sense, I'm just restricting the set of my output. So classification should really think as just a special case of regression. And so if it's a special case of regression, maybe I can just use the previous technique we have seen in the previous lectures with Martin. So is it possible? So, how would you use some regression technique in order to solve a classification problem? What will you do? Do you have some ideas? Mm-hmm. So that's a good idea. Can you say more in details how will you do? How you will do? Okay, I give you like a training set. And you have a training set, for example, you will have your X and you will have your Y. Some Y will belong to the class 1, some other Y will belong to the class 2. What will you do then? Okay, but if I want to compute the optimal weight with this square, I need some output Y, which are real, which are some real number. So now I only have class 1 and class 2. So what can I do? Then that maybe, but my problem is not that the range is not good. My problem is that I just have class 1 and class 2. What does it mean to solve a least square for X belong to the class 1? It's not difficult. Huh? So you can just say that the class 1 will be the value 1 and the class 2 will be the value 0, for example. Okay? So then you are solving your least square. So you will get a vector W. You can get some prediction, W transpose X. It will some value. What will you do with this value? How will you say if X belongs to class 1 or if X belongs to class 2? How do you choose the threshold? Yeah. So what we will do, we consider our training set. We will consider y to be equal to 0 if x belongs to the class 1, and y will be equal to 1 if x belongs to the class 2. Then we will just run some least square solver as before. And then the problem is, how can you do a prediction with this? How can you predict a class? You know, you don't want to predict a value, you want to predict a class. So you want to go from some value. The value will be W transpose X to some class. And so what you will do is that you will use a threshold. If the value is smaller than 0.5, then you will predict the class 1. And if the value is larger than 0.5, you will predict the class 2. Okay? That's a good way to solve it. I mean, it makes sense. So what we want to see now is that, you know, is it a good idea? Do you think it will give us some good results? Or will we see that, in fact, classification maybe is a little bit more complex and we have to think a little bit more and we have to derive some new techniques? So let's see. So is it a good idea first? So what we are doing is that we are considering the previous data set, okay, about the credit card default. And what I told you is that, in fact, one of the features was not informative. So now I'm only considering the balance features. That's the one which will help me to do some prediction. So I have my data set, I have my xn, I have my yn. We say that the xn is the current outstanding debt of my customer. The company has collected a lot of data, okay? We have a lot of this xn, yn. And so y will be equal to 1 if the customer did default, and y will be equal to 0 if the customer did not default. Okay, and what we want to predict is, if I'm giving you now a new value, so I give you a new customer with a new balance, you want to predict if this customer will make some, will default or not. And you can imagine that will be very useful for some bank or some credit card company, okay? So what we did is that we say that all the previous customers who did not default, we put them to the value 0. All the ones who did default, we put them to the value 1. So these are my data. And now I will learn a least square fit. Okay, I will just learn this function. Okay, and then the question is how we will use this line. So the first thing is, how did I learn this? I just, minimize my least square error. So I just minimize the square distance between the line and all my points. This is a least square setting. And how should we use this line? I'm just take a new point, for example, here. I look at the value on this point. It will be exactly equal to 1. 1 is larger than 0.5. So I will predict that this customer will default. Now, if I look at a point here, for example, I can look at the value of my prediction at that point. It will be around 0.4. 0.4 is lower than 0.5. So I can predict that this customer will not default. And so you see here, in this dashed line, it is the decision boundary. It is exactly the frontier between the customer who will not default. So that's the one for which the balance is smaller than this value. And if your balance is above this value, you will be predicted to default. Okay. This is clear. And when we look at this line, we could think that it is working quite well. No? When we look at where we find the decision boundary, it really makes sense. You see that around here, you have a lot of points. Around here, you have a lot of points. So if I would have, ask you, where would you put this decision boundary? I think maybe you will have, you will have gave me an answer which will not be too different from that one. Yes? And so you can see that it's convenient also to predict, to interpret as probability the value of the prediction. Because if it's smaller than 0.5, we predict 0. And if it's larger than 0.5, we predict 1. So in some sense, maybe what we are trying to do is that we are trying to learn what is the probability of making a default or what is the probability of not making a default. So do you see a first problem with this interpretation? Well, it's kind of weird to interpret this value as probability. Exactly. So first, it's a little bit weird to say that these are probabilities because they are not restricted to be between 0 and 1. So we see that it does not make a lot of sense. So that's the first problem. But can you imagine some other problem why, in fact, this is not a great idea to try to solve the classification problem as a regression problem? What could have happened? Yeah. Okay, but do you think this point will be an outlier? I mean, you're right, it's sensitive to extreme value, but the point you are talking about is not an outlier, in fact, and we will talk about it. So that's a very great remark. Do you see another, maybe another reason why it's not a good idea? Sure. Okay. But then if it's nonlinear, then we will have to do something very more complex, But the first example is, in fact, the data set I was showing to you was very well balanced. And that means that I had the same number of customers in the class 1 and in the class 2. But I mean, I lied to you because, in fact, when I'm looking at the original data set, in one of the first plots in the course we saw in the lecture, I only had 3% of customer in the default case. So my two classes were highly unbalanced. And so here you look at what is happening if I'm considering the same data set, but in an unbalanced case. So I will have 15 times more customer in this class than in that class. Okay? And here again, what you are doing is that you are learning your least square fit. And you see now that your line has shifted a lot. And if you look at your decision boundary, whereas when you are looking at at the data set, you don't really see the difference, and you will still be willing to do your threshold around this value. If you are looking at the output of your linear fit, you will be thresholding at this value. So you see that it does not make any sense. If I give you a customer whose balance is more than 2,500, I think that no one in the room will say that this customer will not default. Whereas if you look at the prediction your linear fit is giving to you, that the least square solver is giving to you, it is telling you that you will not default. So you see that the position of the least squares fit really depend a lot on how many points you have in each classes. And that's something which is not a good features of a classification method. Is it clear? Yeah. What does it mean to learn a different threshold? So how would you learn the threshold? Yeah, so that could be an option. That would be kind of also the same, just to, you know, weight your point differently. So you have to, I mean, sure, you have some way to solve this problem, but you see that it's still a bad feature. And what will be even worse is that what you say previously, that in fact, the position of the line really depends a lot on where the point lie. So for example, here I'm taking this, I have the same data set as before. And what I'm doing is that I will add some points with very large depths, okay? And some other point with very negative balance, okay? So I'm faking some customers. Some of them will have a very large depth. Some other of them will be very rich, okay? I mean, it's not a question of wealth, but their balance will be very negative. And now I'm still learning my least square fit. Do you see how much the line has shifted if you compare the blue one, which was without any extreme value, and the orange one? So here it's a little bit hard to see what is happening, so I'm just doing a zoom in the second pictures. Okay, so this is just a zoom between the value 0 and the value 3000. So you see that now, if I want to look where is my decision boundary, so in fact, this line is almost horizontal. But in fact, for all these points, it will be below 0.5, and it starts to be above 0.5 after this threshold. So you see that by adding these points, I'm totally faking my classifier. Because now I will predict as not making default some point for which I'm almost sure the customer will default. Okay. And so previously, one of you said that these points were outliers. So do you, yeah, question? So yeah, I mean, we will, it does, but the difference is that for regression, this point will be outliers. Because for regression, if you have some point with very extreme value, kind of that means that they are not following your linear model assumption. But what I want you to see, and that exactly my question is like, for classification, do you think that these points are outliers? What are these points? These points are customers. They have a very large balance, and they are making default. So do you see that this is not outliers? That just, you know, some person who just spend a lot of money and they will make default. But you should not think of them as outliers. If I ask you to predict them, you will predict them totally correctly. So this is really inliers with extreme value. And in fact, if you think of these points, these are some points which are very easy to predict. So they should not be problematic for your methods. So, you know, we see that the position of the line really depends on where the point lies. What is the value of the balance? And so then the question is why, you know, why it is not working to use least square regression in order to solve classification. And I mean, the reason is that in fact, the criteria we are minimizing, which is a square loss, is really not the loss you want to minimize. I mean, you don't care about the least square, I mean, about the square distance between your prediction and the value of y. This is not what you want to minimize. What do you want to minimize in the classification problem? Yeah, exactly. What you want to minimize is the number of errors you are making. And you are not caring about the distance between your predicted value f and the value y is equal to 1. You know, this is not related, this distance, to what you want to predict. What you really want to minimize is the number of errors you are doing. So you just want that all these points belong to 1 and all these points belong to 0. Okay? And so you see that also this is another problem with the least square. When I'm considering the square loss, then I will suffer the same error if I am above or if I am below, okay? Because the quadratic loss is just y minus y prime square. So for the square loss, it will be exactly the same to be above the line or below the line. But for a classification problem, if I am above the line, I will not do a wrong prediction. I will still do the correct prediction. So I should not suffer any error if I am above the line. So you see that really that the quadratic loss is not a good loss for the classification problem. Okay. If we have a prediction function, it can have a very large mean square error, but still it can be a very good classifier. So in some sense, when for this classification problem, we are trying to minimize the square errors, we are working too hard for the problem we want to do. So sure, in some case, if you find a classifier which will have a very low mean square error, it will give you a good classifier. But in some other case, by trying to push down the mean square error, you are not minimizing the good objective, and it will not give you a good classifier. So we see that if formally classification is a particular case of regression, it will not be enough to use the methods we have seen for regression, and we will have to work a little bit harder and to derive some new methods. And this is what we will do today. So what we will try to see is that really, how can you solve a classification problem? You are observing some points. For example, here you have two classes. You will have the red stars and the blue circles. And you want to find an algorithm which will help you to predict the value of a new point. Okay, this is really the task we are doing in classification. And what we will see today is that we have a lot of different approaches to do so. And we will not review them exhaustively. We will just provide a quick introduction to all of them. And then during the following lectures, we will go more into details and we will really analyze all these methods. Okay, so today is really like a quick introduction. And just if we want to summarize all these methods, you know, what are we really trying to do when we are solving a classification problem? We are really trying to separate the space into various decision boundaries, decision regions. This is really what we are trying to do. We are trying to find some decision boundary which will help you to predict if you belong to the class blue or to the class red. Okay? So what is the first algorithm we will talk about? It is called the nearest neighbor. And you will see it's kind of simple, but it's very nice. And so we will spend a whole lecture on it, not Thursday, but next Tuesday. Okay, and we will really analyze how well it can work. We will derive some precise theoretical result on it. We will be able to be very precise. But first, let's try to define what is the nearest neighbor rule. So if I'm giving you this data set, Okay, so you have a data set with very simple case, 2 classes. I have my blue circles and I have my red stars. And now I give you a new point, that one you see in green. And I want to predict what is the class of this point. What would you say? So who thinks that this point will belong to the class 1, to the blue point? Can you raise your hand? Okay, and to the red one? Okay. So you all think this point should be red. So why do you think it should be a star? Now, how have you made your decision? Someone? Okay. And why the nearest neighbor should be, the correct prediction? What are you assuming? So what you are telling me is that it makes sense to predict this point as a star because we are talking about nearest neighbor, so we are assuming that this point should behave as its neighbor. But you can see that for a lot of problems, if I want to classify you, you won't be classified as your neighbor in the room. Okay. So what are you assuming? We are really assuming that nearby points are likely to have the same label. Okay. Yeah. So we will come to it. So then your question is, what do we mean by nearby? So imagine that you have some distance. It can be the Euclidean distance, it can be any distance, and that for this distance you will have some spatial correlation. So that means that your neighbor is very likely to have the same label as you. Okay. For example, in this room, your neighbor is very likely to follow the machine learning course. You see, that's an easy one. But then you could imagine a lot of other features, for example, gender. If you look at your neighbor is not sure, it will help you to predict your gender. So how can we formally define what is the nearest neighbor? It's really that you are assigning the label of the closest point in your training set. So you have a training set. This is my training set. I take a point and I will look at what is my closest point in my data set. And now I will look at the output, I will look at the label of this point and I will predict exactly this as my label. So is it clear for the definition? Yes? You have a distance, you look at your closest neighbor and you assign the same label. And of course, it will only make sense if we are assuming some spatial correlation. So what are the positive and the negative points of this method? So one of the positive points is that you see there is no optimization involved, or there is no training. You don't have to train a classifier. Okay? I just give you a data set, and with this data set, you can directly do your prediction. There is no pre-computing. So that's something which is very nice. And also, it's kind of very easy to implement. It's very easy to understand. You just look for your closest point in your data set, and you give the same output. So no optimization, easy to implement. And what we will see is that, in fact, this method will work very well for low dimension, for space of low dimension. Okay, so for 1D, 2D, 3D data, it will work quite well. And why? It's because really you see that doing the nearest neighbor rule, you will be able to model some very complex decision boundary. So if you look at this problem, you know, and you were trying to use a different algorithm, it will be kind of hard to get such non-smooth decision boundary. So, you know, but with the nearest neighbor rule, it will be really easy. You just look at the closest point and you predict accordingly. So you see, like by defining implicitly the output, it will really help you to have this weird decision boundary, and this will explain why this method works so well in low dimension. But then what are the negative points? The first one is that it will be very slow at query time. If you compare this to, for example, what we saw previously with using linear regression, previously I just had to compute the value of W transpose X, and then to look at, is it larger or smaller than 0.5? So you see that this is like kind of like a constant time. If I give you W, you will pay O of 1 in order to do your prediction. But now, when you want to do nearest neighbor, what you will have to do is that you will have to look at all your points in your data set in order to find the closest one. So if you are just doing like an easy implementation, each time you will want to make a prediction, you will have to pay a cost of order the number of elements in your training set. So that will be very slow at query time. And then the second point is that what we will see is that this method is not working for large dimension space. So if I have a large, if I have some data which are highly in high dimension, it will not work at all. So do you have an idea why? Why in a high dimension space, in a high dimensional space, it will not work? Before the break. Someone? What is happening in high dimension, which is not happening in low dimension? Yes? Exactly. In a large dimension space, you will be very unlikely to have enough data points in order to cover well your space. So when you will look at your closest neighbor, in fact, it won't be close to you, but it will be in another city if you want. So it will not be predictive at all about your label. You see, this rule is really working well in this, for example, 2D example, where I have a lot of points. And if I take a point, I will be very likely to find a point which is very close to that one. But if, for example, you know, I wanted to predict the value of this point, you directly see that in my training set, I don't have an example which is really close enough to be predictive. So in high dimension, you won't have enough points in order to cover well your space, and this method will not work. Okay, so let's do a quick break, and we start again in 15 minutes. Thanks. A lot of cases, it was better to try to work a little bit harder and to derive some new methods. And the first method we have introduced was the nearest neighbor, where when we are assuming some spatial correlation, so when we are assuming that the points which are nearby are likely to have the same label, then we saw that it makes sense to assign the label of the closest point in your training set. Okay, so that was a simple definition of the nearest neighbor rule. And then we saw that this simple method have a lot of positive points. It was very easy to implement. It did not require any optimization or training procedure. And it worked quite well in low dimension. And even in low dimension, it will be possible to model some very nonlinear, some very weird behavior. But then we saw that this simple rule was not always a good idea. First, because it was very slow. When you want to do a prediction at query time, it will, in general, cost you O of n, where n is the size of your training set to do your prediction. Then we saw that it was not good at all for high dimensional data. And why? It is because in high dimensional space, the distance, the average distance between 2 points will be very large. And so you will be very unlikely to have a neighbor, I mean, that your closest neighbor will share some similarity with you. Okay? So this is why it is not working well in large dimension. And then what we will see now is that also the problem of this method is that the choice of the distance will be really crucial. And so that's another parameter to be considered. Okay? So you have really to, you have to be careful about which distance are you considering when you are implementing this rule, and it will have some importance in your performance. Okay, are all these points clear? In particular, is a point about why it is bad, I mean, why this method is not working well in high dimension clear for all of you? Because maybe this is not so easy. So if we want to do it again, in a low dimensional space, so for example, in this room, it's very likely that your neighbor will share a lot of similarity with you, okay? But then if you assume that your data set is different and that you are only assuming, you are only observing 1 inhabitant of Switzerland, 1 inhabitant of France, 1 inhabitant of the United States. So if you take the closest neighbor, it will be in another country. And so it would be less likely to share some similarity with you. And that's exactly what will happen in a high dimensional space. The distance will be very large. And when you will look at your closest neighbor, it will be very far away. And so it will not share some similarity. And it will not make sense to predict your label to be exactly the same label as your neighbor. Okay? And so why? It's because in a high dimension space, you won't have enough points to cover well all the space. But we will talk more about it next Tuesday. Is it clear for this rule? Yes? Okay. So of course you could say that, why are we only using our closest neighbor? No, we could easily extend this rule by considering k of them, and then we will just do a vote between them. And what we will output will be the majority vote among the k nearest neighbor of your point x. So instead of trusting your closest neighbor, you will ask a little bit around and you will do a vote. And this will be how you will do your decision. Okay? So here we see in the same data set another example. What I will implement is the 3 nearest neighbor rule. So I take a point. I will look around to find the 3 points which are the closest. These are these 3 points. And I will do a vote among them. You see that 1 say you should be red, and the 2 others say you should be blue. So when you do a vote, when you take the majority, you will predict this point as a blue. Okay? So this is a simple generalization. And then the question will be, how do we set the value of k? That will be one of the main questions of the k nearest neighbor. And we will talk about it next week. And we will see that this value of k will be related to the bias trade-off variance we talked about last Thursday. And then you see that, of course, maybe it's not, a very good idea to do a majority vote. Or maybe if you are looking at some, for largest number of points, maybe to the 10 nearest neighbor, it does not make sense to give all of them the same weight. And so that will be another generalization, which is called smoothing kernel. And so smoothing kernel will really be, you will do some weighted linear combination of elements. So you will trust more the advice of a neighbor which will be close, and then you will decay the weight for some neighbor which will be further away. Okay? But other than that, it will be exactly the same method. It does not change a lot. So this is like a simple generalization of this method. We can do it again. You can consider not only your closest neighbor, but you can consider k of them, and you just do a majority vote to decide the label. And then an easy generalization will be not to do a majority vote, but just to do a weighted linear combination of the output. Do you have some questions about this rule? Okay, and if you have some other question, we will talk a lot about them in 1 week. And now, for the last part of the lecture, what we would like to talk about is another classification family, model family, which is the one where you are assuming that your decision boundary are linear. Okay, that could be another idea. You could consider that your classifier will have some linear decision boundary. So in dimension 2, it will be a line, and in larger dimension, it will be an hyperplane. And so how you will do your prediction, we can do this drawing. I have one W, okay? So this is my vector W, and this vector will define an hyperplane. That will be all the points which will be orthogonal to this W. So this is my hyperplane in red, in green. And you see that this hyperplane is derived by my orthogonal vector W. And so how I will do my prediction, I want to say that if I have on one side of my hyperplane, here I will be red, okay, I will be a star. And if I am in the other side of the hyperplane, I will be blue. I will be a circle. And so what does it mean to say we are on one side of the hyperplane or we are on the other side of the hyperplane? It's exactly the same as looking at the scalar product between x and w and to look at the sign of this value. Okay, because if you think about it, the scalar product between x and w, it's exactly the cosinus of this angle. And the scalar product between w and x2, it will be this scalar product. So you see that if you are on this side, then this scalar product will be positive. Whereas when you are on the other side of the hyperplane, your scalar product will be negative. Okay? So when we are talking about linear decision boundaries, we are really talking about finding a vector W such that you will do your prediction using the sign of X transpose W. I give you a W, you want to make a prediction, you will compute X transpose W. If this is a positive number, you say it belongs to the class 1. And if it is a negative number, you say it belongs to the class 2. Is it clear? Yeah. In that setting, I do not allow for any offset, but you can always add a small shift term W0. Okay. But I mean, we will talk also about it Thursday when we will talk about logistic regression. Often what you will do is that you will add constant features in your X and you will put the offset on X. But that's a very good comment. I mean, it makes no sense to assume that your hyperplane is necessarily going through 0. So you can add an offset to play with it. So maybe one comment you could do is that it's not a good idea to do linear prediction. If we come back to the previous example, for example, for this kind of data set, of course, if I try to do a linear decision boundary, it will not work well. But what we could, kind of think of is that maybe in very large dimensional space, then the geometry will be a little bit different and linear decision boundary will work not too bad. Okay, so this is what you have to have in mind. And then what we also see is that considering linear decision boundary will be really easy to do the training. So we will talk about it, but it will be very easy to learn your weight W. And also prediction are really easy. If I give you W, it's very easy to do a prediction. You just have to compute the scalar product and take the sign. Okay, so you see that it is working quite well. So let's see then, how we can find a good hyperplane. So for simplicity, we will first assume that your data set is linear separable. Okay. So what does it mean that the data set is linearly separable? That means that it exists a separating hyperplane. And so what does it mean? It means that it exists one hyperplane, for example, that one, such that all the blue points are on one side of the hyperplane and all the red points are on the other side of the hyperplane. Okay? So you see that a separating hyperplane is really an hyperplane which will help you to get perfect prediction on your data set. If you were predicting the label of your training set using this hyperplane, you will get a 0 classification error. All the blue points are on this side and all the red points are on the other side. Okay, is it clear for the definition of a separating hyperplane? And so when one separating hyperplane exists, we say that the data are linearly separable. So, of course, it makes sense if your data are linearly separable to output one separating hyperplane. It will not make sense to use this hyperplane to make your prediction, because even on your training set, you will suffer a lot of error. Okay, all these points will be badly classified, and all these points will also be badly classified. So if your data set are linearly separable, you want to output one separating hyperplane. But then maybe you will directly see it. If it exists one separating hyperplane, it's really likely that it will exist a lot of them. For example, this will also be a separating hyperplane. That one also. You have a lot of them. And so the question will be, which one to pick? What does it mean to take the best one? Okay, so what we just say is that if it exists one separating hyperplane, it will exist a lot of them. And now the question is, how should you choose one separating hyperplane? What does it mean to choose the best one? Now, what will be the definition of best? What do you want for this hyperplane? Because all this hyperplane will get 0 training error. Okay, but if we go before this, what does it mean to take a good hyperplane? What do you know, what is a property? We talked about it last week. But this is a geometric interpretation, but you know why? Why would you like to be the furthest away to all the points? Exactly. So you want to find an hyperplane which will have a good generalization error. So then what does it mean? So, you know, for example, these are my training sets. But if I look at a point around here, it's very likely that this point will be blue. And if I look at a point around here, it's very likely that this point will be red. So these are the points, you know, which are easy to classify. And you want to find a point, an hyperplane which will help you to do such good classification. But if now I look at, you know, for example, this hyperplane, you see why this hyperplane is not a good idea. Why in practice I will prefer that one. Yeah? Yeah, but you go too far away. You know, okay, minimum distance, but why, you know, why this will not be a good idea? It's really because my data, I mean, my distribution is very concentrated around here. So when I'm predicting this point or around this point, I know that they will be blue, and here I know that they will be red. But when I'm look, you know, a little bit in the center, it's not clear at all what will be the label. So maybe sometimes I will observe some blue points here. Sometimes I will observe some red point here. And so you want to find an hyperplane which is robust to this kind of stuff. You really want to find an hyperplane which will help you to do a good prediction and which is kind of consistent with what you are already observed. And so the concept behind this and the concept behind how to choose this hyperplane is exactly what you all say, is this concept of margin. So that will be very important. So what is the definition of the margin? If I give you an hyperplane, here this is this hyperplane in green, the margin will be the distance between the hyperplane and the closest point on my data set. So you look at your hyperplane, you look at all the distance between your point and your hyperplane. So for example, you have that one, and that one. And the margin will be the minimum distance between all your point and the hyperplane. So in that precise case, you see that the margin will be exactly this distance. Okay? Is it clear for the definition of the margin? The margin is a minimal distance between your hyperplane and your training set. So it is well defined. And then what we will see is that it makes sense to take the hyperplane which has the largest margin. That means that to take the hyperplane which is the furthest away of all your training points. So this is what is called the max margin separating hyperplane. Okay, you will take the hyperplane which will maximize the margin. So that will be the hyperplane which will be the furthest away of all the points. So why do we want to take that one? Is such that we will be as robust as possible because we will be very far away from the blue point. So if I see some point, for example, here or here, and they are still likely to be blue, I will classify them well. And that's exactly the same for some other point around here. They are far away for your training point, but they are still likely to be red because they are in some sense closer to the red point than to the blue point. Okay. So what we should think about it is in some sense, if I compare this hyperplane in red, which is my max margin hyperplane, and I compare it with this hyperplane here in blue. So you see that the margin of this hyperplane is really smaller, okay? If I look at the distance between the smallest distance between this hyperplane and the training set, it will be this distance. Yeah. Can you repeat again? Sorry. So you say what, that the margin is not well defined, or that the maximum? No, it's not unique. Okay, but you have to pick one max margin. But I did not say that it was unique. But for each hyperplane, the margin is well defined. Maybe it will not, maybe you will have 2 points which will be at the same distance of your hyperplane, but still this distance will be well defined. So for each hyperplane, you can associate it to its margin, and then you can look at all the margin for all the hyperplane, and this you can take the minimum value of this, and so but the argmin is not necessarily unique, but you take one hyperplane whose margin will be minimal. Okay. Very good point. But so what we wanted to say is that in that case, this will be one max margin hyperplane. And I want to compare it to this hyperplane in blue, for which it's clear that the margin is smaller. Okay. The margin is this distance for the blue hyperplane. It is smaller than this distance, which is the margin of the red hyperplane. And so why these hyperplanes makes more sense is because you see that here, I'm very likely to observe some blue points here. And for all these points, if I'm using the blue hyperplane, I will predict them in red. Okay. Whereas it makes no sense to predict these points in red. Whereas when we are considering this max margin hyperplane, you see that in fact all these points, you will classify them as blue. And this makes a lot of sense. Okay. So what is important to have in mind is really that in comparison to all the other separating hyperplane, the max margin one will be the one which will be the less prone to errors. Okay. If you are slightly changing your training set, if you are like wiggling the input a little bit, then when you will do your prediction using the max margin classifier, then the number of misclassification will stay low. Okay. So is it clear about this max margin separating hyperplane? Do you see why kind of it makes sense if you have the choice to choose one separating hyperplane to take that one? Yes? And so we will talk again about it in 2 weeks. And so what we will see is that there is one particular algorithmic way to find one hyperplane, which when the data will be separable, because in all generality, maybe your training set will not be linearly separable, but when your data will be linearly separable, this hyperplane will be the max margin hyperplane. And so this method is called the support vector machine, and it is one of the most famous classification algorithms, and we will devote one lecture about it. And also, logistic regression in some sense is related to the max margin hyperplane, and we will talk about it Thursday. So do you have some questions? No? Okay. But if we consider a more general setting, of course, you know, the data won't be necessarily linear. And if I look, for example, at this example, it will not make sense to look for a linear classifier. If you take a linear classifier, any linear classifier will always suffer from a very high error. So what is the next step? So the next step is to consider nonlinear classifier, as we have done in regression. You know, why do you limit yourself only to hyperplane if you could predict such more complicated shape? So in the regression, we have already seen one easy way to introduce some nonlinearity, but still learning a linear classifier. Do you remember how you did that? Can you say it louder? Exactly. So the first way is to use some features augmentation. Instead of only using the features, you will consider some, for example, in that case, polynomial expansion. So you will add x2, x3, you will add some monomials. And then you will learn a linear classifier, but on this extended space. Okay. And what is very interesting is that even if you have learned a linear classifier for these augmented features, when you will look back at the projection only in your initial features, then it won't be linear. And this was exactly what we did at the beginning of the lecture. I can show you again. That one, when I told you that this was nonlinear, in fact, this classifier is obtained by learning a linear classifier on some augmented features. So if you look at the shape of the function in your augmented space, it will be linear. But when you project it back in your first features, you will obtain some nonlinearity. Okay, so that was one way to consider nonlinear classifier. But then, you know, like the problem, and also like some of you came at before the course to talk to me about it, when you will add some features, then you will augment your space. And then also the complexity will go up because you are adding more and more features. So then the complexity of the method will increase. And it will be more costly to train your model. And so what we will see in one of the next lecture is that it's possible in some way, by considering what is called the kernel method, to augment the features up to some infinite dimension without incurring the cost of adding these extra features. So by doing kernel method, in some sense, we will benefit the joy of the high dimension, but we will not suffer the price. And the only downside of this kernel method will be, it will not be possible to add all the features you want, but it will only be possible to add the features in one particular way. So we will talk about also in a few weeks about these kernel methods. And so, do you have some questions about nonlinearity? No? And if you have some, we will talk a lot about it during the kernel course. And so in the last 10 minutes, what I would like to talk to you a bit is a little bit about the theory of classification and what can we prove and what can we say about this problem. So, as in regression and as in the last lecture, what we are assuming is that the X and the Y are distributed according to some distribution D that you don't know. D exists, but you do not have access to D, to your distribution. And we say that X will belong to some space X and Y will belong to some space Y. And in that precise case, Y would be equal to 0, 1. Okay, it could be -1, 1, it could be anything, but let's talk about just binary classification. And we call the labels 0 and 1. So what are you doing is that you are observing your training set, x1, y1 to xn, yn. And this training set will come from the same distribution D. It will be IID realization. And you want to use this training set to learn a good classifier. And so what does it mean in that sense to be a good classifier? What we saw in the generalization lectures, the first thing you have to define is which loss function you want to use. And so for regression problem, we say that we want to use a quadratic loss. So I remind you that the quadratic loss was a squared before y and y prime. So it was y minus y prime squared. And so the loss is really like the loss you are suffering when you are predicting y prime, but your true value is y. And so when I'm considering classification, what is my loss function? This is very important. This is what is called the classification loss. And so you see, that's really intuitive that the loss, that the indicator of y is different from y prime. So if I'm doing a good prediction, if I say that the label is y prime and that the same label of y, so I have assigned the correct label, my loss is 0. I have done a good prediction, so I should not suffer any loss. But if my prediction is different from y, so for example, if y was equal to 0 and I'm predicting 1, then I will pay the price to be 1. So you see that the loss function is really exactly what you would like to be. If you are doing a mistake, you are losing 1, you pay 1. And if you are not doing any mistake, you are losing nothing. So this is what is the loss function, the classification loss. Is it clear for the definition of this loss? Yes? This is really natural. It's really what you want to do. You will pay something if you are doing a mistake, and you will pay nothing if you are doing the good prediction. And now what we can look at as last time is the true risk, okay, or the generalization error, you can call it as you want, for the classification. So let me remind you what was the true risk. It was really the expectation over all your observation, x and y, of your loss function. So the true risk was really the true risk of a classifier G is really like the error you will suffer in average. So you look for an average x and the average output y. You look at the value you are predicting with G. Okay, so the value you are predicting that exactly g of x, and you look at if g of x is equal to y or is different to y. If g of x and y are equal, then the loss will be equal to 0. And if they are different, the loss will be equal to 1. And then what you are doing is that you are taking the expectation over all the possible realization of x and y according to your distribution. So you see, this is really what is called the classification error. Okay? That the true risk or that the generalization error associated with your classification problem. And then we see one nice trick is that since this is the expectation of an indicator function, you know that is exactly equal to the probability. So you see that for the classification loss, the classification error is exactly the probability that y is different from g of x. Okay? So your classification error is equal to the probability of making an error. And so what does it mean to find a classifier which will generalize well? That means that you want to find a classifier for which the probability of making an error is as small as possible. Does it make a lot of sense, no? Yeah. Sure, the expectation of an indicator function is always the probability of the event of the indicator function. Okay. So maybe some first question, know why, I mean, we will not talk a lot about it, but why in order to find a good classifier, why are we not directly minimizing this function? Why are we not minimizing the expectation of this loss function? Do you have an idea why? Why are you not doing your gradient descent algorithm on this loss function? Yeah. So you see that this loss function is very nice, is very intuitive, but it is not differentiable. It's even not continuous. So this is why we are using this loss kind of to evaluate the performance of your classification, I mean, of your classifier, but we will not use this loss in order to find a classifier. And so then the question is, we have defined what is a classification error of a classifier. So is it possible to derive what is the best classifier possible? Okay, even imagine that you have an infinite training set. I imagine even that you know the distribution D. What is the best you can do? Okay, if you know the distribution D, how will you predict what is the output Y when you observe one X? So this is what is called the bias classifier. This is really like the best classifier possible. Okay, so that's the classifier which will minimize your true risk over all the possible classifiers. That means that you can have all the information you want, you can have all the training data you want. It will never be possible to predict better than your bias classifier. And the last result, I mean, the first result and the last result we will see today is that you have a closed form for this best possible classifier, for the bias classifier. And this closed form is really saying that G star of X will be for any point X. You look at the probability of Y equal to, so okay, so small y can be equal to 0 or 1. So for example, you will look at the probability that your true output Y is equal to 0, knowing that your input is X. This will be equal to some value. Then you will look at the probability that your output Y is equal to 1, knowing that your input is X. This will be to another value, and you will output the maximum of these two values. Okay, you will output the Y, which give you the maximum of these two values. So the interpretation should be clear, is that given a fixed X, the probability that the correct label is Y, then this probability is exactly P of Y knowing X. Okay? So if the prediction is G of X, then you will be correct a fraction P G of X knowing Y. And so if you want to maximize the probability of being correct, you really want to maximize this function. You want that your output will be the value which will maximize the probability of being correct. So this is your bias classifier. So we won't have time, but in the slide, you will find a formal proof of this definition. We can just do it quickly together. The first claim will be that first you can fix X. That's the same when you are fixing X to look at this argmin, then it will give you the best classifier. And the second claim will be exactly what we just saw, is that G star of X will be the argmin for all the Y of the probability that Y is different than Y. So you can look at the proof. It's not difficult at all. And if you have some question, we will be able to answer them next time. And just to tell you, you have some bonus in the slide. It's not important at all. Let me just tell you about this result. This result will just tell you that it is possible to theoretically show that if you have some function which is good for the regression problem, then it will be good for the classification problem. So that's really show what we have seen in the first part of the course, is that if you have some regression function for which you will have a small regression error, then it will imply that the classification error will be small. But what is important is that it's possible to have a small classification error, but a large regression error. Okay, so that does not contradict what we say. That does not say that all the regression methods are good for classification. It is only saying that if you have one classifier which will have a very small mean square error, then it's possible to prove that the prediction error for the classification problem will also be small. Okay? So thanks, that will be all for today. Please do not forget to register to the lab, okay, before tonight.